Now, color, and color magnitude diagrams in the infrared. All right, so remember this movie? Remember that the infrared bands are falling comfortably on the Rayleigh-Jean side here. Remember that, at least until the mid-Ms, the slope isn't changing. So the ratio of the fluxes isn't changing. So the color isn't changing. So that means that when we have color, and color magnitude diagrams in the infrared, we're looking at totally different parts of the SED. So most stars that don't have dust have really zero color in IRAC, MIPS, and Ys. I don't mean that the measurement in one band is zero, but the difference in bands and magnitudes is zero for stars that don't have dust. Things that are not stars without dust don't have zero color. You find IR color magnitudes all over the place, much more frequently than optical, but color magnitude diagrams are still everywhere too. The near-infrared color, and color magnitude diagrams are ubiquitous in many papers because the two-mass data are widely available and used everywhere. They come in a wide variety of types, some of which in the literature can be very, very confusing. I'm going to use some plots that I made for my NITARP team that studied AFGL 490, and I'm also using plots from the literature for those just for comparison. So this is two-mass data for AFGL 490. So I've got J-band here and H minus K on the x-axis. So again, remember the numbers are increasing going down because I want bright objects at the top. So reddening is going to make me fainter and redder. So this time reddening is pointing down and to the right. The main sequence here is very much more vertical than it was in the optical, but it is not yet exactly vertical. It will be before we're done with this section. It is much more vertical because of where, the J-band and K-band fall in this plot. Okay? So it's pretty close to vertical, especially for the higher mass. Fainter things have more scatter, which is not surprising. There are lots of red things and lots of red and bright things, and the red and bright things are likely the young stars, but some of them are background giants. So this is K versus H minus K from one of the literature papers in 2008 on AFGL 490. And they actually put indications of spectral types on their main sequence there. They added in some isochrones, and they plotted some of their stars. They added a reddening vector there at the top. And they called out the names of some of their targets in here too. See, red and bright things are their young stars. Here's a color diagram from two mass again. So here's J minus H versus H minus K. So now the numbers are increasing properly, mathematically correctly, increasing up and increasing to the right. And reddening is going to push us redder in both of these axes, so up and to the right. Here's the main sequence. Look, it's curving back on itself. So the colors are not going to tell us automatically anything about the temperature. The dot dash lines here are extensions of where the main sequence is. So in other words, anything that falls between these two dashed dot lines are conceivably just reddened main sequence stars. So in other words, like this guy is, if you push him back parallel to the reddening vector, he could end up here. He could end up here. We don't know if he's a low mass or a high mass star, but anything between these two lines is plausibly just reddened main sequence stars. And we get a lot of scatter in here. We get a lot of stuff over here and a lot of stuff over here. Stuff over here should not be there. Stuff over here, though, are young stars. This is red in both axes and reddened here. These are the young stars. This is another paper studying this target, AFGL 490 from literature, J minus H versus H minus K. I don't know exactly what they've put here, but you can see, again, they've added a reddening vector, and they're telling you where they're looking for the young stars. This is a different star-forming region called NGC 1333, and this one is an IRAC color diagram. So we've got 3.6 minus 4.5 on the y-axis, and 5.8 minus 8 on the x-axis. Stars that have zero color are the stars without dust. They're just photospheres. So what are all the other things? They're the young stars. So in order to figure that out, we can do models. We can make models. This is from a paper, Allen et al. In 2004. 3.6 minus 4.5 versus 5.8 minus 8. Stars, photospheres, no dust are here. And this is where all of their models are. You've got envelope models and disk models. But they're showing you, in this case, the reddening is not up and to the right, it's up and to the left because of that giant silicate absorption line. Turns out that affects 5.8 and 8. So that's why you end up and to the left, not up and to the right. And they've got two different reddening laws here. That's why they've got two different reddening vectors. But basically, things that are red in both of these colors are class 1s. Things that are not quite as red are class 2s. So this is combining those things together. This is real data, 3.6 minus 4.5 versus 5.8 minus 8. These are photospheres. These are class 2s. These are class 1s. And the reddening vectors here are showing you that these are reddened class 2s. These are reddened class 1s. Make sense? Okay, so this is IRAC data from AFGL 490. Stars without dust are near 0. Reddening is up and to the left, as in the other versions of this plot, 5.8 minus 8 versus 3.6 minus 4.5. Look how tiny this is. This is 10 magnitudes in the optical, but this is a plot in the infrared, so it's a tiny impact. Stuff that's up and to the right in both axes are the young stars. So the takeaway points here, remember, colors are differences in magnitudes, which are ratio of fluxes. Plots of colors and magnitudes help you study the properties of objects you know, and then you can apply those properties to understand the nature of objects you don't know. So for IR points, because the IR bands are largely on the Rayleigh-Jeans side of the SCD, the IR colors are going to be 0 for stars without dust. In other words, things that are just stars without dust, plain stars. Colors that are not 0 tell you about things that don't look like plain stars. So the infrared colors and magnitudes are going to help you find stars with circumstellar dust, but you can be confused because they're going to also find active galactic nuclei, asymptotic giant branch stars, and other things that are in the way. We'll talk about that next.